Hi guys, as I promised, we're going to look at a few free response questions together. This is one of the few ones that we did not discuss in class. For this particular 10-point problem, we have a projectile motion problem. A ball of mass 0.5 kilograms initially at rest is kicked directly towards a fence from a point 32 meters away, as shown above. The velocity of the ball as it leaves the kicker's foot is 20 meters per second at an angle of 37 degrees above the horizontal. The top of the fence is 2.5 meters high. The kicker's foot is in contact with the ball for 0.05 seconds. The ball hits nothing while in flight and air resistance is negligible. This is actually a very old question from the release questions. The reason I know this is they've provided you the values of sine and cosine and tangent for the appropriate angle. That means this predates the use of calculators, or at least graphing calculators, on the free response. So I think this one is about as old as I am, or at least this could have been my free response question back in high school. So I think this one's late 80s, early 90s. It doesn't matter. It's still a viable question, only they wouldn't give you the sines and cosines. First thing, determine the magnitude of the average net force exerted on the ball during the kick. Alright, so it's not moving, now it's moving, therefore we have some forces involved. We could possibly look at this from the work kinetic energy theorem and say there's some work done on the ball giving it this kinetic energy, but that doesn't quite work out because for that we would need to know the distance through which he kicks. If that's what we were given instead of the time down here, that would be our approach. Instead, we want to look at this thing from the point of view of impulse and momentum. Okay, so we've got impulse is equal to a change in momentum. The change in momentum is the final momentum minus the initial momentum. The initial momentum is nothing. So our final momentum is the mass times the velocity at which it's kicked. I'm just going to call that V naught here. So we have V naught at that location. We're given time. Now we can find the force. The force is therefore going to be the mass times that original velocity divided by the time it took to kick it. The mass was 0.5 kilograms. The velocity was 20 meters per second. Don't care about the direction. We just want the magnitude of the new momentum. The time involved was 0.05 seconds. And so we end up with 20 times 0.5 divided by 0.05. I know I could probably do that in my head. As a matter of fact, we've got 0.5 divided by 0.05, so that could reduce down to 1 over 1/10. 20 divided by 1/10 is 200, which is our answer. Like I said, I think this one predates use of calculators, so they expected longhand. Alright, we got kilograms times meters divided by seconds squared. Oh yeah, that's right, we call that newtons. Alright, and that would have got you 3 points. Next part of the problem, we want to determine the time it takes for the ball to reach the plane of the fence. For this, we only want the x component of the velocity. If we call the 32 meters x, and of course we have the x component of the velocity, which never changes, so I'm just going to call that v sub x. And v sub x is, of course, the adjacent side of the triangle. So cosine has adjacent involved in it. So my delta x is equal to v sub x multiplied by t. We actually want to solve for t. T is equal to delta x divided by v sub x. V sub x, on the other hand, is v naught times, we decided, cosine was the correct way to go. Cosine of our 37 degrees. So delta x is 32 meters. V naught was 20. And that was meters per second, of course. And our cosine of 37, they gave it to us up there as 0.80. And so down here we get times 0.80, so that'd be 16. So we have 32 divided by 16. So we can get that our time is equal to 2 seconds. It is only in the air for 2 seconds before it gets to where the fence is located. Now, of course, the final question is what, as would be expected with them having drawn in the fence, will the ball hit the fence? If so, how far below the top of the fence will it hit? If not, how far above the top of the fence will it pass? So we are looking for delta y, right? We are not sure exactly where this guy is going to hit. It's going to come over here, and at this point here, this is my delta y. It might be greater than 2.5, in which case it misses the fence. It might be less than 2.5, in which case it hits the fence, and we'll have to compare it to the height of the fence. Our delta y occurs at 2.0 seconds. So we can go back to our kinematics, and our kinematics for, I'm looking for my equation sheet. I figured I'd start from their version of the equation. Let me grab one. Sorry, guys. Should have had that ready. All right, here's our equation sheet that we've got. When we want to know distance in terms of initial velocity and acceleration, and we know the time, this is a good choice for it. So we're going to start with that, and I'm going to transpose that into terms of y. I'm taking my y naught over there. Y naught is equal to Vy initial times time plus 1/2 the acceleration. This is in the y direction, so that's g, multiplied by my time squared. My Vy initial is going to be equal to the initial velocity times the sine of 37 degrees, because earlier we decided that this guy was going to be based on cosine, so that means the vertical one is going to be based on sine. Let's double check. So katoa, sine is opposite side, that's over here. Vy initial, or we could put a naught on it, but I like initials. They'll work with either one as long as you're consistent. Alright, so that's equal to that original velocity times the sine of 37 degrees multiplied by our time, 1/2 g times t squared. I don't see a request any place for using 9.8, so I'm going to use, actually, because we're trying to really decide if it hits the fence or not, and it might be really close, I am going to use 9.8. So delta y, all right, so plugging in values here, V naught is 20 meters per second. Sine of 37 degrees is 0.60 times our time of 2 seconds plus 1/2. Actually, now that I'm thinking about this, since this was pre-calculator time, they probably requested at the beginning of this thing that you use 10.0. So I'm going to change that over to 10.0. 10 meters per second squared multiplied by our time of 2 seconds. And I guess I should have been going 2.0, but that's fine. Again, they're a little loose with their significant digits. As long as you don't overexpress it by more than 1, they're okay with it. Be careful here. This is the y direction only. That means going up needs to be consistently positive or negative. Going down needs to be consistently positive or negative. I'm saying that up is positive, down is negative, so that means my acceleration from gravity is negative. All right, since we are doing this with, and I got to square my time over there. All right, theoretically, this was pre-calculator. So 0.6 times 2 is 1.2. 20 times 1.2 is 24. So I've got 24 meters per second. That doesn't look right. Nope, it's not meters per second. Seconds on the top. Seconds. Numerator, denominator, cancel out. 24 meters minus, because one of the terms is negative. 1/2 times 10, that's a 5. 2 squared, that's 4. 4 times 5 is 20. 20 meters. So my entire delta y is 4.0 meters. Okay, my delta y is 4.0 meters, so it clears the fence. By 4.0 meters minus the 2.5 meters. If I want it, they're going to forgive you subtracting off one simple number. Clears the fence by 1.5 meters. And if you really wanted to, you can say 4.0 meters minus 2.5 meters. Okay. Clears the fence. Whoops. A little sloppy there. By 1.5 meters. They do like your answers boxed in. And that's the end of the first one. Sorry if it took a while.